calculate L, and we see that L is equal to h bar multiplied by the square root of L multiplied by L plus 1, where L, once again, is the orbital quantum number. Now, if we take this L in this equation and replace L with this, we get the following equation. So this equation gives us the electron's magnetic dipole moment in terms of the orbital quantum number. So mu is equal to negative E, the charge on that electron, multiplied by h bar divided by 2m, where m is the mass, multiplied by the square root of L, multiplied by L plus 1. So this equation gives us the magnetic dipole moment of the electron moving about the nucleus of that atom. Now, what happens if we take our electron that is spinning, so the electron has a spin, that creates a magnetic dipole moment, and now we take the electron and we place it inside an external magnetic field. So let's suppose the direction of the electron's magnetic dipole moment points along the following axis, and let's suppose we place it inside a magnetic field B that points upward as shown. As soon as we turn this field on, basically this magnetic field B will exert a torque on this electron's magnetic dipole moment mu, and it will orient it. The torque will basically move it and align our magnetic dipole moment along the same axis as the direction of the magnetic field line. So when an electron with a magnetic dipole moment mu is placed into an external magnetic field B, the magnetic field creates a torque that acts on the magnetic dipole moment of the electron to orient it along the magnetic field B. Now, we can choose the direction of the magnetic field to be any direction. Let's suppose that the magnetic field points along the z-axis. So let's suppose this is our z-axis. Now, if we turn on that magnetic field that points along the z-axis, what will happen to the angular momentum L of that electron? Well, basically, the angular momentum of that electron will orient itself along with the magnetic field. So that means if the magnetic field points along the z-axis, this angular momentum will also point along the z-axis. So that means the L angular momentum will point along the z-axis, and that's exactly what this subscript means. So L subscript z means the angular momentum of that electron points along the z-axis. Now recall in our discussion on quantum numbers we said that L subscript z is equal to the product of our ML, which is the magnetic quantum number, multiplied by h bar. Now, if we take this equation and replace the L with this quantity, we get the following result. And notice we place a z